All right, hey everyone. So this is gonna be walkthrough videos for the questions that we didn't go over. And so just as a reminder, these are the ones that we didn't go over. So question one, recursion, mutation, trees, linked lists, and regex. And so yeah, let's get started. And so by the way, I don't have access to a tablet anymore, unfortunately. So I'll do my best to like help you visualize things, but just so you know, you won't have any nice drawings this time. But yeah, so starting with question number one, this is like paths. And so what it's gonna do is like x is like our starting value, and y is the value that we want to end up at, and we wanna figure out all the paths that we can take with a combination of either adding one or doubling it. And so as you can see, from 3 to 5, notice how you can't really double 3 as it will go above 5. And so 3, 4, 5, that's the only path you can do. And that's by going one at a time. And on the other hand, if you had like paths 3, 6, there's like two different paths. You could double to 3, or you could just add 1 a bunch of times. And then paths 3, 9, there's a bunch of different values. And notice for each path, it's going to be the starting value each time. So that's going to be x, and the ending value y each time. And so yeah, think about let's take a little bit of time to like working it on your own, just like a couple hints. If you want to pause the video if you don't want these hints. But here we have like a good skeleton code that we can make use of. And so here we have like two if statements, if and an elif, and they go directly to return values. And so if they go directly to return values, then it might be a base case, so consider that. And otherwise we have A and we have B. And so think about what A could be, what B could be, and usually these do refer to like recursive calls or something, and think about how you can combine that answer in the end. And since we have two choices here, incrementing or doubling, think about what that could refer to, what type of recursion that might be. And yeah, pause the video, work on it for a few minutes, and we'll go over it right now. And so here, we want to consider these two base cases. So if something, return something, elif another base case, then we return something else. And so one of the situations that we might want to consider is that, we're going from 3 to 5, and let's say 3 goes to 4, 4 goes to 5, and once we reach 5, so for example, when x is equal to y, so 3 is equal to 3, then we know that there only is one path left, and that path is going to be just the number 3. And so what we're going to do here is we're going to say if s is equal to y, then what are we going to return? Well, we want to return a list containing the only path, and that only path is that 3, 3 thing. Is that just the value 3? Because we're already at our destination. And so what we're going to do is we're going to return a list containing a path, which is a list containing the value x. And so notice how x is equal to y, that's our destination. And then otherwise, we need to consider another base case. And so if you think about something we did previously, and it was like count stairways or something, and we had this idea that we have like, here, let me try to draw a stair. Might not be the best stair, but let's try it out. So all right, we have our stairs right here, and one of the things to note is that let's say we're on this step right here, and we could either take like 1 or 2 steps, and if we take 2 steps, then we overstepped and we don't want to count that. Well, same principle applies to paths, this path problem right here. So if we have the 3 right here and we double that 3 and we get 6, well, 6 is greater than 5, and so we don't want to include that. And because we're gonna have no paths for like, if I were to have like paths from like 6 to 5, then there would be no paths, because there is no way for that 6 to get to a 5, because you can only go up or double it, and that means that your x can only increase. It can't go back down to 5. And it's because of that, that's another base case. So if x is greater than y, then what are we going to return? Well, we're going to return an empty list, and that's saying that since it's empty, there are no paths for going from x to y. And now we want to handle our base case. I mean, our recursive call. And so going back to this idea that we can either increment x or double x, that gives an idea as to like what our recursive calls might be. And so they're both going to be calls to path. But the thing about this is that we want to supply different values of x because we're changing that value x. So that 3 might turn into a 4 or it might turn into a 6 by doubling it. And so what's going to happen here is that we're going to call paths on x plus 1 and y. And this represents incrementing x by 1. And on the other hand, another like choice that we can take is by doubling x. And so b is going to be paths x times 2 comma y. And so this is doubling x. And then so here, let's use this example, paths 3, 9. Actually, let's use paths 3, 6. This is a bit smaller. And so I'm going to comment this out, paths 3, 6, and it should return the list like 3, 4, 5, 6, and 3, 6. And so let's consider what each of the recursive calls are going to do. So paths of 4, 6, well, you can't double 4 to like go back, because that's going to get you to 8, which is above 6. But paths of 4, 6, we expect it to return the value 4, 5, 6, because that's the only path. And then paths of 6, 6, so doubling that 3, what is it going to return? Well, it's going to return just the 6 because we've reached our destination and there's only one path, which is starting from that 6. And if we notice, these are all valid paths to go to 6, from 4 to 6 and 6 to 6. And if you think about this, so one path was to go to 3 to 4 to 6. And so paths of 4, 6 represents the path from going from 4 to 6. And so we know that going from 3 to 4, that's like only adding 1. And we added 1 right here. So that counts as a valid path. And all we need to do is add that 3 to the beginning of that list. And same with path 6, 6. We add that 3 to the beginning. And we get our final answer if we join these two lists as like the list 3, 4, 5, 6 and 3, 6, the two paths. And so that's what we're going to do for this problem. And so A gives you the path from like x plus 1 to y, and B gives you all the paths from x times 2 to y. And what do we want to do? Well, first we want to join these two like lists together. And so here what we get is that like if I were to use this example, we would have a list with like 4, 5, 6 and a list containing 6 in that total list. And then what do we want to do? Well, we want to add 3 to the beginning of each element of that list. And so what we're going to do here is we're going to have a list comprehension. And then so we're going to go through each possible path. So for P in A plus B. And so A plus B is going to be a list containing all the paths, including the ones from like x plus 1 to y and x2 to y, x times 2 to y. And what we're going to do, we're going to add 3 to the beginning of it. Or x, the value of x that we have currently. And so it's going to be x plus that P, that path. So we're adding x to the beginning of that path. Remember that the path is a list. And if we want to add an element to the beginning, we have to enclose it in a list and do like list addition. So we're going to add x to the beginning of that path. And for P and all of the possible paths going from x beyond. And so yeah, and if we were to run this, hopefully I didn't mess up anywhere. Did I mess up? Okay, I did not. And so yeah, that's going to be the paths from. And once again, if you have any questions, just feel free to let me know. And here is the solution that they have right here. And it's like pretty much the same thing. They switched around the base case. And yeah. All right, moving on to the next part. Question number 2, reverse. And so what reverse does is it explicitly tells you that this is a mutation problem. And so what it does is that it reverses the elements of the list. And then so what's going to happen right here is that we have original list. And if we call reverse on it, it's going to mutate it. And if we check what the original list now, notice how we didn't reassign original list to like a result of reverse like this. Like that. And it's because of that we can tell that this is going to be a mutation problem. Well, they tell you right here, but if you want to be able to tell, that's how you can tell. If we check what original list is now, we can notice that all the elements have been reversed. And then in the case of an odd list, the the 72, the middle element, does not get changed, but everything else gets swapped. But yeah, let's take a little bit of time, work through it, and we'll go over it real quick. And so I guess one hint I could give is, what is the index of the first element and what is the index of the last element for any list of any length? And then after we get those elements, how do we swap it? And then yeah, work through it real quick and let's go over it now. And so what we want to know here is that for any list, let's say it's like A, B, C, comma Z. The first element is going to be 0, and the second element is, the last element is going to be -1. And then the second element is going to be 1, and the last element is going to be, it's going to be -2. And so let's say we have the elements 0 and -1. Then what we can do afterwards is we can swap these two elements and then move on, and then swap the 1 and the -2, and then swap the 2 and then the -3 until we swap everything. And so here, let's say we were trying to swap the first index element, whatever index element x. And so x might be 0, and we want to swap it with -1. And then so how are we going to pair up 0 with that -1 and 1 with that -2 is, notice that it's the negative, except you like subtract one more. And so 0, -0, that's just 0. You subtract 1 to get -1. 1 to get -2, you would multiply it by -1 and subtract 1. And so that's how we're going to get the corresponding opposite element of that list. And so here we have an index x. I'm actually going to name it I. And then to get the other element, our index of the other element that we're trying to swap, we do -I minus 1. And then so we have list indexed at I and list indexed at -I minus 1. And well, how can we swap it? Well, we can swap it via doing this. List of I, the first index element, and like the opposite element, -I minus 1. We can say that's equal to the other element. So list I becomes list of I minus -I minus 1. And then list of -I minus 1 becomes list of I. And so yeah, that's how we're going to swap a certain index element with the opposite element of that list on the other side. And so for example, swapping that B with maybe like that Y right there, the second to last element. And so yeah, so we have that swap, and now we want to like swap every single element. And then so what we're going to do right here is we're going to say for I in range of list. And there's something wrong with this. We'll go over it real quick. But the idea here is that like, it's going to start off with element 0. We're going to swap the 0th element, A, with the last element. And then we're going to go to the first index, which is B. We're going to swap it with -I minus 1, which is -2, which is Y. And we're going to keep on going and on. And we should swap every single element. Oh, I forgot to say length of the list right here. Not the list. So remember that you have to pass in like the length of the list rather than the list, because range takes in a number. But yeah, and then so there's one more thing to note about this code. There's something wrong. And so what we want to notice is that like if I had like the list 1, 2, 3, what would happen is that we would swap the 1 and the 3, so it becomes 3 and 1. Then we would swap the 2 and the 2. Well, it's gonna be pointing to the same thing. So like the second to last element is gonna swap itself, and so nothing's gonna happen here. But then we swap that 1 with the 3, so it becomes 1 and 3 again. And if you notice, it's the exact same list as before. So what we want to do is we want to do that first original swap, so like swapping the 1 and the 3, but we want to stop halfway through, so we don't end up like switching these elements back. And so what we're going to do with this range is that we're going to take that length of the list and divide it by 2. So notice how this is integer division. So you want to pass in like an integer to range so that it doesn't do like a range of 2.5. I'm pretty sure this doesn't work, but yeah, you don't want to do that. And so pass in range of length of list divided by 2, and this should work, hopefully. Let's check it out. All right, yeah, so it ends up working. And if we were to look at our code right here, they do a, like, switch it up a bit, like by changing, rather than using negative indices, they use like the actual index of the list. But this is pretty much the same thing. Take a look at it, try to understand it. But yeah. And so next up is going to be the function reverse other. And so this is a tree problem, and what's going to happen is that it's going to reverse the labels on every other odd def tree. And so if you notice, once again, I don't really have a tab. Oh, I guess I could use this tool right here. So if I had like 1, 2, 3, 4, and so what's going to happen here is that this is a def 0. Let's say the top is def 0, and right here, wait, okay, never mind. Let's say the top node is def 1. And so we see that the top node is def 1. And what's going to happen afterwards is that we see it's def 1, it's an odd def. Let me actually make a bit more. And so what's going to happen here is that since it's an odd def, we're going to reverse the label of all the branches. And so that 2, 3, 4, well, that becomes 4, 3, 2. And then this is def 2. And so notice how 3 and 2 don't really have any branches, so we don't care about that. But for this branch right here, it's an even number def. And so we don't want to reverse the labels right here. So the 5 and 6 stay as it is right now. They don't become 6, 5. And you can imagine that's def 3. We're going to reverse the labels of the branches if there are any. Def 4, we don't do it. Def 5, etc. And yeah. And so yeah, think about how you want to solve this problem. Once again, it is trees, so you will be using recursion. And one hint I have is that every other branch, every other def. And so the thing to know about this is that every other def, well, how can we tell that it is every other def? Because if we make a call to reverse other, called on a certain tree, now how can we tell that this tree is an odd def? So we need to be able to supply that information somehow, and think about how you can do that. And yeah, let's work on it for a little bit, and we'll go over it together. But yeah, let's start out. And so there's this idea that every other odd def level. And so every other odd def level, how can we do that? And so it turns out that if we want to supply that extra information on whether it is an odd def, we're going to have to make a helper function, because we only have one parameter t, but we want to be able to pass in like whether it's like on an odd def or not. And so helper of t and odd, essentially. So that variable odd is telling us whether we're on an odd def or not. And if you imagine, if it's odd, then we like swap around labels or something. And if it's not odd, then we don't do anything. But yeah, and so if you imagine at the very end, we want to call our helper function. And then calling our helper function, we want to call it on t. And then we want to say whether that top node is odd or not. And so for the case of this problem, we define like an odd def level, the top node to be at an odd def level. So we want to pass in true. And then so what's going to happen here is that in the helper function, so like the main block of our code, is that if it's odd, then we want to swap around our labels and all of that. So like turning the 2, 3, 4 into the 4, 3, 2. And then afterwards, we want to go ahead and make our recursive calls on the branches. And so, this diagram's still here. I don't know if you can read it, but hopefully it makes sense. And so what happens here is that if we're at the top, that one right there, it's going to handle like reversing all of the branches, right? So like the 2, 3, 4 became like the 4, 3, 2. And then what the recursive calls are going to do, the recursive calls are going to handle like mutating the other branches all the way down below, everything below this. And so if you might imagine, if we made a recursive call to that 4 branch right here, what's going to happen is that it's going to handle reversing the labels of all of the other branches, all of the nodes under it. And if we made a recursive call 3, it would handle everything under that. Same with 2. And so that's how we're going to use the recursive calls to handle like mutating our entire tree. And then so you can imagine, typically with every single tree problem, you're usually going to see like 4b and t dot branches. And then what we're going to do here is we're going to call helper of b, that branch. And then since we're like going from odd def to an even def, you want to essentially like flip that odd. So for example, if we were at def 1, you swap around the nodes, and then we go into an even def, we want to turn that odd into a false. And if we went from even to odd, we would turn that false into a true. And so we're going to pass in not odd right here. And yeah, and so we handled the recursive calls. And now what we want to handle is the labels. And so the question is, how do we switch labels? And so first of all, how do we get a list of the labels? And so the idea here is that we're going to get a list of the labels. And then we're going to go through each branch and get like, give it like the new label that we want to give it. And so first, let's start off by getting the list of labels. And so how do we get the list of labels? Well, we have the branches. So if we were to use this example up here, the branches are like 2, 3, 4, and we want to get the 2 and the 3 and the 4. Notice how we're mapping it to some value. And so we probably want to use a list comprehension. And so we're going through each branch. So for b and t dot branches. And what do we want out of it? Well, we want the label of it. So tree of 2, if we were to say like t dot label, we would get that value 2 out of it. And so we're going to say b dot label for b and t dot branches. Labels equals that. And then, there are a lot of ways you could do it. But for this case, I'm going to reverse the labels list right now. And so you can imagine if I had that 2, 3, 4, I would turn it into a 4, 3, 2. And when I'm going through each of the branches, then I would be able to like give the first branch the value 4, then the second branch the value 3, etc. And then so how I'm going to reverse it is there are a lot of ways, different ways you can reverse it. For example, you could use this previous code up here to like reverse the list. But what I'm going to do is I'm going to use list splicing. And so you don't really need to know too much about how this works. But if I provide : -1, it does reverse the list. And so yeah, once again, there are a lot of different ways you could do it. This is just one of many ways. And so yeah, and so now we have a list of reverse labels. I'm going to call this reverse labels. And what I want to do here is I want to go through each branch and assign it like the new label. And so I'm going to go like, and the thing to know about this is that we actually need the index. So for example, if we were on the first element of the tree, we will need to know that it's the first element to like match that label with that tree. Because for example, if I did like for b in t dot branches, well, what happens here is that we have that branch, but we don't know if this is like the first branch, the second branch, the third branch, and so we can't get the right label from it. Because like for example, if we were on the second branch, we wouldn't be able to tell that, oh, we're supposed to get this 3 out of the reverse labels. We would have to know the right index. And so because of this, we can't do like for b and t dot branches. We have to use like the indices for I in range of length of t dot branches. And so if t dot branches was like the list, like tree of 2, tree of 3, tree of 4, what will happen is that the length is 3, and it'll go like 0. Index 0 corresponds to tree 2. Index 1 corresponds to tree 3. Index 2 corresponds to tree 4. And so yeah, and we would get the corresponding branch via doing like t dot branches indexed I. And so we have t dot branches indexed at I, and we want to change the label to be that reverse label of that corresponding index. So what we're going to do is we're going to say that branch's label, so that tree's label, is going to be equal to reverse labels index.I right there. And so yeah, that's going to be how we're going to reverse it. And that should be everything that in our code. And hopefully this works. I kind of winged it. And yeah, awesome. And so once again, what happens is that if it's odd, then we reverse the labels of those branches. And the recursive calls handle like reversing all the other nodes under those branches. And once again, since we had to pass in the information on whether that tree was at an odd depth or not, we created a helper function with the original parameter t, and we added that parameter odd to tell us whether it was odd or not. And yeah, so here's the solution right here. And take a look at it, try to understand it. And if you have any questions, feel free to email me. And yeah. All right. And next up, we have multiply links. And so how multiply links is going to work is that you have like a list of linked lists. And so, for example, we have A equals length of the elements 2, 3, 5, B is 642, C is 4102. And we multiply, we pass in those values as a list, and it's going to multiply. We're going to get a new linked list out of it. And the first element is going to be 2 times 6 times 4, so that's 48. And notice P dot first is 48. And then 3 times 4 times 1, that becomes 12. And then 5 times 2 times 0, that becomes 0. It doesn't say in the doc test, but you can imagine that. And then, but the thing is, it only multiplies like the elements in which every single linked list has an element for it. And so it doesn't end up multiplying this link to by anything at the very end of C, because B doesn't have a fourth element and A doesn't have a fourth element either. And so, yeah. And so how we're going to start out, actually, a couple tips, I guess, is that think about what your recursive call might be. And so I guess one hint might be maybe your recursive call might be handling like one element of the final list at a time. So one recursive call might be handling 48, another recursive call might be handling 12, and we might reach our base case at some point. And so, yeah. And then so take a minute and we'll start now. And so the idea behind this is that each recursive call, I guess you have to choose between whether it's like recursive or iterative. But in this case, you could probably tell that it's recursive a little bit because you kind of see this for loop. And so you can infer a little bit that, you can't iterate through a linked list. So you're probably going to be iterating through like that list of linked lists. And so you iterate through the list of linked lists, and you might like multiply like the 264, but then you don't really have much space else in your code to like handle like multiplying 341 to 520 and all of that. And so because of that, this problem is probably going to be recursive. And then so what's going to happen here is that each recursive call is going to handle multiplying like one element at a time. It's like the 2 times 6 times 4 becomes the 48. And then essentially what we want to do for each recursive call is that we want to remove that like the first elements of each list. So like becomes like a link 3, 5, 4, 2, and 1, 0. And if you're thinking about that, if we were to imagine what this recursive call might do, we would return the linked list 12, 0 with the elements 12 and 0. And what we can do is we can take that original product 48 and like add it in. So it becomes like 48, 12, 0. And so, yeah. And once again, the idea for our base case, what we want to note is that we stop whenever there are no elements for like another linked list. And so notice how C has like 3 elements remaining, B only has 2, A only has 2. And so if you imagine our recursive calls take another link out of A each time, take another link out of B. So A and B after like a couple more recursive calls becomes like link.empty, while C still has link of 2. And so because A and B are linked are empty and there isn't anything else to multiply, then that's going to be our base case right here, because what we want to end up with is link.empty because there are no numbers left to multiply. And if you imagine, we get link.empty and we're going to chain the other elements to that link.empty. So if you might imagine, it's like link of 0, link.empty, and we're chaining that 12 in. So link of 12, the product of those elements, the second class elements, and then like we're going to chain that 48 from the very beginning, the product of the first elements. And that's how we're going to go about creating our linked list. And so, yeah. And so starting off, we want to keep track of like multiplying the 2, the 6, and the 4 together. And so how we're going to do this is that we're going to use like a product. Keep track of like a product maybe. And so prod, we're going to say that it's going to be 1. And if you imagine, what we're going to do is we're going to multiply that 1 by 2, becomes 2. Multiply 6 becomes 12. Multiply by 4 becomes 48. And that's going to be our total product. And so, yeah. And so for this for loop right here, we're essentially going to go through each element of the linked list. I mean, the list. So like A, then B, and C. And we're going to multiply each of those elements, like values together. It's like the 2, the 6, and the 4. And so that's going to be for L and K in the list of linked lists. And then so we're going through each list, and then we have this if condition right here. We can go back to it after we finish everything up. And then what we're going to do is we're going to multiply that product by the linked list value. And so going back to this if statement right here, what we want to note is that if any link is link.empty, so let's say we like made our recursive calls A is link.empty, then we're done because we don't have any values left in A to multiply, and so we should stop there because that's how this problem works. That whose a linked list whose length is that of the shortest linked list given. And so if this linked list is link.empty, then what do we want to do? Because there are no elements left to multiply, we want to return link.empty. But otherwise, we want to like go ahead and multiply that value with the product. And so at the very end, then what do we need to do? What we need to do is we need to make a recursive call to multiply links. And so, oh shit, oh man. Let me bring that value back, that value of A. Okay. Then we're going to return link.empty. And yeah, we're back where we are. And so yeah, and so what happens here is that we're gonna have a recursive call that handles like multiplying like 3, 5, the 4, 2, and the 1, 0, 2. And so we need to remove the first element of each of the linked lists and make a recursive call on the list with like the first element stripped, taken off. And so what it's going to be is going to be multiply links of a list comprehension. And so what's going to happen here is that we have like a bunch of linked lists as from that list right there. And so what we're going to do is going to say for a link in that list of links. And what we're going to do is we're going to say link, we're going to map it to link.rest. And so what it's saying is like .a.rest, that's going to be link of 3, 5. B.rest is going to be 4, 2. C.rest is going to be 1, 0, 2. So we're removing that first element. And if we were to make a recursive call to that with the first elements removed, you can imagine it's going to be link of 12 and link. It's going to be a linked list with like 12 and 0. And then afterwards, we're going to add that 48 in that product to get 48, 12, 0, like that. And then so we're going to assign that recursive call to a variable called rest. And then at the very end, what we're going to do is we're going to return a new linked list containing that product and the rest of the elements. So it would, up here, we would essentially be saying link of 48, and the rest of the elements are that linked list 12 and 0, and that would turn it into like 48, 12, 0, like that. I switch keyboards. But yeah, so this is gonna be multiply links, and if you want to see the solution right here, that is solution. They switch around some orderings with the list comprehension right here. But yeah, same idea. And so here is an iterative solution. I did not know there's an iterative solution. Oh, okay. This does not really fit the skeleton, and this is quite a convoluted solution. And so, yeah, so from the skeleton right here, you can't really do it iteratively. But if you're ever interested in the iterative solution, then take a look at this, try to understand it, and if you have any questions, feel free to like email me. But yeah. And so now we have a function called non-decreasing, by non-decreasing. And what's going to happen here is that we have a list 1, 2, 3, 4, 1, 2, 3, 4, 1, 1, 1, 2, 1, 1, 0, 4, 3, 2, 1. And now it's going to group it into lists that are like non-decreasing. So if you go like 1, then 2, then 3, then 4, you know, those are all increasing. But if we go from 4 to 1, that's decreasing. So we're going to separate the two. So it becomes like a list 1, 2, 3, 4. And yeah, that's like the basic premise of this problem. And 1, 2, 3, 4, 4 going to 1, that's decreasing. So, you know, we don't really want to include that. So we split. And so 1, 2, 3, 4, then 1, 1, 1, 2. Note that 1 going to 1, that counts as non-decreasing. So they're grouped together. 1, 1, 2. But then it goes from 2 to 1. So we split it up there. 1, 1. Then it goes to 0, 0, 4, 3, 2, 1. But yeah. And so I guess a couple hints to get started, if you want to hear, is that if we have like the list of 1, 2, 3, 1, you can imagine that with this non-decreasing list, that there's like a recursive call that we have to make. And typically with like scheme, you do it on like the executor of that list. And it might vary from time to time. You might not do it on the executor, but let's imagine if we did it on the executor of the list. So if we made a recursive call like 2, 3, 1. And so what do we expect that to return? And then and so by the way, the final result of like the first call, we should expect to get like the list 1, 2, 3, and 1. And the list 1. And so we have that. And then for the list 2, 3, 1, what do we expect the recursive call to be? And how do we add that 1 back in to get this answer right here? And in addition, if we, for example, let's make more recursive calls. Let's say we have 3, 1. Yeah. So what do we expect this recursive call to return? Actually, let's make it just a 1 right here. Yeah. So what do we expect this recursive call to return? We made a recursive call 3, 1, and the 1. What do we expect the recursive call on the list 1 to return? And how we add that 3 back in to get, you know, you expect like 3 and 1. And so, yeah, take a little bit of time, try to think through it, and I'll go over it right now. And so, yeah, and so what we want to know here is that the list 2, 3, 1, so going over this example, is going to turn into the list 2, 3, and 1. And so how do we add that 1? Well, the 1 is supposed to belong in the sequence 2, 3. Because 1 to 3 is non-decreasing. And so in that case, what we want to do is we want to add that 1 to the beginning of the first element of that list. So the list 2, 3, add the 1 to the beginning, and that should be what we want to get. But on the other hand, if we had the list 3, 1, and so the recursive call to 1 is going to end us up with like the list containing the list 1. But notice how 3 and 1, those don't belong as part of the same sequence because 3, 1 is not non-decreasing. And so we want a brand new list. And so in this case, if we see that 3 is greater than 1, then we want to create a brand new list and add it in. But on the other hand, if we see that as part of the non-decreasing sequence, so 1 is like less than or equal to 2, the first element is less than or equal to the second element, then we want to add it into like the first current element. And so yeah, that's kind of going to be the premises of how this is going to work. And yeah, let's get started with our skeleton code. And so first of all, we can probably go over the base case later. And so this is, you can imagine that this is going to be the recursive call. And so what we're going to do here is that we have a let expression. And so we can figure out what we want to use this left for, because it's like variable assignments. We can like kind of determine that later. But let's start with this if condition right here. And so our if condition right here is whether the first and second elements are like greater than the other, or etc. And so this corresponds to like to two cases, right? So if the 1 is greater than the 2, then we want to 1 is less than or equal to the 2, then we want to add that element in to the current like first element. But otherwise, if it's greater than it, then what we want to do is like add it as a brand new list. And so our if condition right here is whether like that 1 is like less than or equal to the 2. And so the first element, how do we get the first element? Well, that's going to be the car of that list S. And the second element is going to be the car of the cooter of that list S. And so if that first element is less than or equal to, then what we want to handle is like adding it into the first element. And so it turns out, just telling you right here, that we actually have to like switch the two cases. So if it's greater than, then this case is handling like the case of like 3, 1. So creating a brand new list. And the second case is handling if we're like adding it to the current one. So we're adding like the 1 to the list 2, 3. And so the reasoning behind this is that we have rest right here. And if we're adding the list 3 to the list 1, well, we can assume that the list 1, that corresponds to like the recursive call on the remainder of the list. And so that means that maybe we should use this rest variable as the recursive call. So we're going to assign it to non-decreased list of the cooter of S. And so what happens here is that if that first element is greater than the second element, then we want to create a brand new list. So we're going to add, we're going to create that list 3, and we're going to add it to that list 1 to get like 3, the list containing 3, the list containing 1. And so what's going to happen here is that we're going to make a list out of that element, list of car S, and we're going to add it in. So so in this case, the rest would be like list 1 containing the list containing 1, and then we're adding, like we're consing that list 3 into that list, and that would get us 3, 1, like that. And so that's what's happening there. And on the other hand, if it is like 1, 2, 3, then we want to add that 1 into the existing list of that recursive call, so the list 2, 3, that is the first list. And so how we're going to do that is we're going to cons that first element, so car S, and what do we want to cons it into? Well, we want to cons it into the first element of that recursive call, rest. And so how we're going to get rest? That element is via car rest. And so I'll comment right here. If you imagine our recursive call to like 2, 3, rest might be the list 2, 3, and 1. And then the cooter of rest is going to be the list containing 1. And then what happens after is that the car of rest corresponds to like the list 2, 3. And if we were to cons the first element, so that's the 1, into that list 2, 3, we would get the list 1, 2, 3. And what's happening is that we're consing this list, which corresponds to that, into the cooter of rest, which is the list 1. So we took out that list 2, 3, we added the 1 in, and we're adding it back in as list 1, 2, 3. And so yeah, so that's kind of like what's happening there. And so yeah, so we handled like the recursive calls here, and now let's handle the base case. And so what we want to know here is that we're comparing the first and second elements of the list. So we might be comparing like 3 with that 1. But what we want to note is that if I have just the list 1 or just the list 0, then what do we want to return in these cases? Because we can't compare like the first and second elements. And so if I were to just have the list 1, well, what do I want to return? Well, I would just want the list 1 like that. And on the other hand, I don't actually know if you need to handle this case, to be honest. Let's check the solutions real quick. Okay, they handle it a little bit of a different way. They handle it in the recursive call. And so what we want to handle, first of all, is if the list is nil. And so if the list is nil, then what do we want to do? We want to just return an empty list because there are no elements to be included in part of the sequence. So we're going to say if null s, then what do we want to return? We want to return just s, which is nil. On the other hand, if it were to like the list containing just the element 1, then we want to have a list enclosing. We want to enclose it with like another list. But as you can see here, we don't really have space for another case. And so the question is, how are we going to handle it? And so what we're going to do here is, if we imagine a recursive call to like the cooter of s, then we're going to get an empty list. And then we want to add the list 1 into there like that. And then so let's take a look at our recursive calls and see what can handle it. And rest is going to be an empty list. And we're trying to cons a list containing that first element, so that 1 into it. So it turns out this handles it for us. So consing that list 1 into an empty list nil gets us the list containing 1. And so we're going to add an extra condition right here. So we want to add the extra condition that if the cooter of the list is nil. Because if the cooter of the list is nil, then what we want to do is we want to add that list 1 to the recursive call rest, which is nil, to get our list parentheses 1 right there. And so we have another condition here, and we want to OR it together. So if it's null, or the first element is like greater than the second element, then we want to go into creating a new list and adding it into the recursive call. And so yeah, that's kind of going to be that problem. I know I think I flubbed a couple explanations. So if you do have any questions, feel free to like email me or something. Oh, I messed up. Remove this right here. Yeah, nice, it works. But yeah, this is a pretty complicated problem. Probably like exam level or like a bit harder. So congrats if you did it. If you didn't figure it out, no worries. All good. Just like let me know if you have any questions. But yeah, oh my god, this is kind of a marathon. I feel so tired right now. But yeah, so now last but not least, we have question number 8, and this is like a phone number validator. And so phone numbers in this case can be either 7, 10, or 11 digits long. And the thing about this is that they can be separated, like, so the idea here is that like if you have 11 digits, you have starting with a 1, like a single digit grouped together, and you have 3, and then 3, and then 4. In the case of the 10 number, it's like 334, In the case of 7 numbers, it's like 3, 4. And the thing about with each of these groups of like numbers is that they can either be separated by a dash or by a space or with just like straight up nothing. And you could even like mix it up if you want. And so yeah, so a couple hints for this problem is that first start out by like representing like maybe a like group of digits. So like 7, 8, 9, 0, those 4 digits. How do we represent it? And then how do we represent, like we can have a dash, a space, or nothing. And then last but not least, we want to be handling like 7, 10, or 11 numbers. And so think about how to make this like 1, 2, 3 dash optional, or like the 1 dash 1 2 3 dash optional. And yeah. And so take a little bit of time, we'll through it, and we'll go over it right now. And so what we want to handle here is, so let's say if we want to like handle 4 digits, like what would the regex be for it? So a digit is \d, and if we want to say we want 4 digits, then what we have to do is the quantifier is a quantifier. So you know, like quantifier is like plus star, but for this case we want to use like the curly braces and 4. So it's saying we have digits, and how many of them do we want? We want 4 of them. And so that's going to represent 4 digits. And so I'm going to get rid of that. And so if you might imagine, if you want to handle 3 digits, then what we would do is we go like digits of 3. And so one thing to note about all the regex for all of these phone numbers, so like 7, 10, or 11 digits, is that they all have like the 3 digits, then the 4 digits right after. So let's handle the regex for that. And if you imagine, we can tack on like the 1, 2, 3 dash, like 3 digits, extra digits at the beginning as optional, as well as the 1 digit at the very beginning as optional. And so how do we handle this? Well, we have 3 digits followed by 4 digits. And the thing about this is that they're separated by you know, a space, a dash, or nothing at all. And so how do we represent that? Well, how we're going to represent it is with a character class that is optional. And so here we can either have like a dash or a space, or we can have just straight up nothing. And to represent nothing, we put the question mark right here. So it's either saying like you can have one of these, it's like a dash or a space, or you could have nothing at all, which is the question mark. Because the question mark says you could have this pattern or you cannot. And yeah. And so now from this, we like matched our essentially our phone numbers that are just like 7 digits. So ABC 123-4, 5, 6, 7. And so now we want to be able to handle like optional parts. And so for example, there's like 2, 3, 4 dash, and I put parentheses around it to like separate it. It's not for any particular reason, but we want to have this like 2, 3, 4 dash. We want to be able to support it, but at the same time it should be optional. And so how do we represent that like 2, 3, 4 dash? Like, you know, it could be a 2, 3, 4 space, or it could be 2, 3, 4 nothing. And then so we're going to represent this regex via like another 3, and that's going to represent like another 3 digits. And so to represent 3 digits, we have \d, quantifier saying we want 3 of them. And then to connect it with that one, like the 1, 2, 3, 4, 5, 6, 7, you know, we can either have like a space, a dash, or nothing. So we're going to use this exact same thing that we had earlier, and we're going to throw it right there. So that's representing like the 2, 3, 4 dash right there. And how do we include it in the expression? Well, what we're going to do is we're going to take this, we're going to copy it in. But the thing to note about this is we can have it, or we could also not have it. Because like in the case of like 7 digits, we don't want to include this right here. And so what we're going to do is we're going to throw parentheses around the entire thing, and we're going to throw a question mark right in front of it, saying this, you may or may not have this. And so yeah, so now we're able to handle 7 digits and 10 digits, but we also need to handle like the last digit, 11 digits. And so let's say we're able to handle like 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. We also want to be able to handle like 8 dash at 1, 2, 3. So that 8 dash may or may not be there. And so we're going to handle that 11th. I'll type out the regex right here. In a similar fashion to how we handled like the 10 digits. And so what we're going to do is we're going to say we want 1 digit. So here we have \d, and we can have like the separator. So like the dash or the space or nothing at all. And so yeah, so that's going to be that right there. And notice how we also want to make it optional. And so you might be inclined to do something like this. So throw it in right there at the very beginning. But there's one thing to note. And this doesn't fully match what we want to represent. And so the thing about this is that since the 11th digit and the extra 3 digits are kind of like separated as being optional, what kind of happens here is that this is unintended. We can have like an 8-digit phone number. For example, like 1, 1, 2, 3, 1, 2, 3, 4. And so because of this, this is not a valid phone number because it's 8 digits. But what happens here is that so this one we decide to include in a regex because we have like the 1 dash. So this is like we decide that this is not optional, we include it. But then we decide not to include this one right there because we have like the 3 digits dash the 4 digits at the end. And so because there's nothing else to match, we don't have any extra 3 digits to match. And so we decide to make this optional. But the thing to note is that the 1 dash always comes with like the extra 3 digits used to make like the 10th digit. So we need that like 1 dash 0 0 dash etc. So that 1 dash always has to come with this regex right here. And so to make that happen, what we're going to do is we're going to take that 11th digit regex and we're going to throw it inside of that optional regex. So what this regex here is essentially saying is that, so starting off with this, the 3 digits dash like the next 4 digits are mandatory. But here, what this is saying is that we can have an additional 3 digits. And then if we have those additional 3 digits, then we can also have an additional last digit, that 1 right there. And so that's what this regex is like representing. That's why you have like so many nested question marks, stuff like that. And yeah, so I think this is going to be it for this one. Oh, actually, there's one more thing. And so one thing to note is that, we have, for example, this example right here. So, clearly this part is like 11 digits, right? But we don't consider this to be a phone number because, there's like hella digits afterwards. And this entire thing is not a phone number because it's way more than 11 digits. And so what we're going to do is we need to make sure that this like phone number is like the start of like a word essentially. So what we're going to do right here. So it's like it makes sure that like this entire thing does not count. So what we're going to do is we're going to throw like a word boundary at the very ends. So saying like this is like the start and end of like a word sequence. And so yeah, so what's going to happen here, we're like escaping the boundaries so that this does not get counted as a phone number. Yeah, and last but not least, we have our regex expression. And so we want to be able to search this string. And so the parameters that you want to pass in is the expression that you want to search a string for and the string you're searching it for, which is the parameter that we passed in, which might be song by logic. And so yeah, and if we were to run it in the code, hopefully not mess up. All right, I did mess up. Let me think about how to fix this real quick. Oh, did I switch up the... Okay, never mind, I didn't switch it up. What did I mess up? I'm goofing. Let's see. All right, sorry about this. I'm a bit bad currently. Oh yeah, if you want to take a look at the solutions real quick, they're right here. I'm guessing these are all alternate solutions, 3 different solutions. And so yeah. Hmm. Oh, all right. Yeah, so don't be like me. What you want to do is, since this is a regex expression, we want to make sure like our escape characters count as escape characters. So the reason behind this is, let me pull up an interpreter. So if I were to say hello backslash x or something like that. Oh, never mind. Backslash or something, it would represent like hello backslash something. And on the other hand, if I were to do the regex for hello backslash, it would be a bit different, because essentially regex does is it escapes those backslashes for you. So that B, if I said like backslash B in regex, when I threw the R at the beginning, it would be counted as like backslash B to represent like an actual backslash in like a string. And so yeah, whenever you're doing regex, make sure to throw that R in front, and hopefully this works now. So that R in front indicates that it's a regex expression. And yeah, awesome, it passes. And so yeah, so this is the end of the final review. If you listen to all of this, I'm kind of amazed. Thank you for listening. Hope you learned something. But yeah, if you have any questions, feel free to email me. My email is powing123@berkeley.edu once again. And yeah, good luck on the final. You got this.